Welcome to the second lecture of week 1, and this lecture will be on stress strain relationship. And this particular lecture I have divided in two parts, where in both part I will discuss stress and strain relationship. In first part we will discuss basic of stress and strain and derive the expression of relation between stress and strain, and in next part we will discuss some of the examples with a few more stresses. Okay. So, let us start with definition of stress. So, you all have the idea what is stress, okay? Because I need to use this stress in determining or in deriving the expression of stress and strain relation. We will recall the stress and strain first. Okay. So, if you see the term stress is used to express the loading in terms of force applied to a certain cross sectional area of an object. So, what is stress? That is basically the force when I am applying a force on a particular object, but in a particular cross sectional area of that object, not in whole object. Whatever would be the cross sectional area and whatever force is applicable to that area, based on that we can define the stress. Okay. So, from the perspective of loading, stress is applied force or system of forces that tends to deform a body. Okay. So, this stress is basically the force or system of forces applied to a particular object till it deform. Okay. It gives the deformation, and that is occurring due to the stress. So, as I have already told that it deforms the body, it deforms the object. So, what happens, how it will deform? It will deform because it will whatever force is applied to a particular cross sectional area, that force will be distributed internally to that object, and if it is stretched, if force is applied to stretch it, for example, if this is the bar, here I am applying the force. So, what happens, it will be pulled or stretched in this direction. So, whatever force I am applying, that is distributed in the distributed internally in this object, and after some time when force will increase, that distance between molecules available in that aparts, or that distance increases, and therefore, the deformity occur. So, according to the stress distribution, we can say the deformity will be uniform or it will be non-uniform. For example, if I am having this bar, okay, and if I apply force to this side or to a given cross sectional area, okay. So, what happens here, like so, what happens here, whatever force I am applying, that would be uniformly distributed in this object. So, according to that uniformity, whatever change will occur, that will be uniform. Like if I pull in this way, the whole section or whole object will have increment in length, not in a particular point. Okay. And in the similar line, if I try to bend it, if I try to bend this or bend a wire, so distribution will be non-uniform, and stress would be higher at center, and it will keep on decreasing as we move towards the bending side. Okay. So, according to the internal distribution, we have uniform change in shape, or that shape may be non-uniform. Okay. And mathematically, if you define the stress, that is force acting on a particular area, we call this as stress, that almost all of us know this. So, that is mathematically it is represented as sigma equal to F by A. Symbol to be used for stress, F is the force applied and A to a given cross section. So, this is the basic expression for step. There are many types of stresses, but primarily we have three types which we will consider in this particular course. The first one is the tensile stress. Okay. Tensile stress occurs when the material is subjected to pulling or stretching. So, if I need to pull the object okay, from one side, that will give the tensile stress in this object, okay. And next stress I am having is the compressive stress. So, what happens? Compressive stress basically works towards the center. Compressive stress, because I am compressing from here as well as from here. If I can compress from both side, or maybe one side is fixed, from another side I am pushing it. So, what happened, that stress collected at the center, okay, and it reduces the length of that object, okay. So, whatever dimension, either tensile or compressive stress will be applied, in tensile that dimension will increase, and in compressive stress that dimension will be decrease. And third stress I am having is the shear stress. So, shear stress is the stress state at which shape of material tends to change, okay, like sliding force. If I am having two objects like this, which are or if I am having one object of this shape, and here I have to apply force in this direction, and in this object I have to apply force in this direction. So, it will be slide over each other. So, in that case, shape of the object will change. In tensile and compressive, shape will remain as it is, and only that dimension where that force is applicable, that will change. If it is a bar, it will remain bar at the end. However, if it is a shear stress, that shape may be changed, okay. So, if you see this image here, we have this this is the original length, that is L naught. This is the original length. When I am pushing that or when I am applying tensile load, we have change in length, that is basically delta L. So, through delta L whole length will be changed. And in the similar line, when I am applying compressive load, or when I compress this, the distance between this overall length will be reduced by delta L. And in sliding or in shear or in tangential stress, we have to apply two opposite forces, and then it changes the shape of the object like this, okay. So, in shear we have volume of the object will remain as it is. So, in shear, volume of the object will remain as it is. However, that volume vary when I am applying tensile as well as compressive. So, it is another example of tensile, like here we have the broken lines at the center. Here again I have a broken line, but that lines are joining each other, and in shear we have the applied forces, and in shear the sliding occur in the object. So, these are different types of stresses. Usually in our day to day life we see example of such stresses, but I can give you a very common example of compressive stress, which I think all of us use, okay. And that can be given through shoes which we are wearing. For example, if I am purchasing a shoe, and at that time when I have purchased that, at that time when we wear that shoe, we have very cushioning effect, very comfortable effect to we observe in our feet. But after continuous operation or after continuous use, use in what way? If I continuously use that in exercising, walking, running, so what happens, whatever material available in the sole, that compact, okay, compaction, or what we say, that the material will be compact. So, after certain time, when it will when that compactness will keep on increasing, that cushioning effect will keep on destroying. So, after continuous operation, that cushioning effect will not be as we have felt at the time of purchase of that shoes. So, this is a very common example of compressive stress, because continuously putting force to that sole makes that sole more compact, okay. Next, we have to define the strain. It is basically generated due to stress, okay. So, strain is basically normal stress on a body causes change in length or volume, and tangential stress produces change in shape. So, this we have already discussed that when normal stress will be applicable, the shape of the object will remain as it is, only that particular dimension will change where that stress is applicable. However, when I am using shear stress, the shape of the object will change. So, the ratio of change produced in the dimension of a body by a system of forces in equilibrium to its original dimension is called strain. So, strain is basically change in dimension divided by original dimension, as you can see here. Okay. So, when the material is stretched, change in length and strain are positive. Okay. So, when we are pulling any object or stretching any object, we have change, whatever change I am expecting, that change is positive. How that change is computed? That final length minus initial length. So, obviously, when we have the increment in length, that delta L would be positive. In the similar line, when I am having compressive stress, final length would be lesser in comparison to original. So, in that case strain would be negative. So, this conforms with the signs of stresses which would accompany the strains, tensile stress being positive and compressive stress being negative. So, when I am having stress, when I am applying tensile stress, the whatever change will occur in strain, that would be positive, and therefore, strain will be called as positive strain or tensile strain. I think you are getting me. And if I am applying compressive stress, it means that change in length would be negative. So, compressive stress will reduce the length and then strain would be negative, and then that strain will be called as compressive strain. And here I am having longitudinal strain. Longitudinal strain means what? If I am having original length L, I stretch this and then increment in length would be delta L. So, delta L by L would be the longitudinal strain, as can be seen from this particular expression. And now we have volume strain. Volume strain means how you can define that? Change in volume divided by original volume. Okay. So, when we have observed change in volume, either I am using tensile stress or compressive stress. So, volume strain would be delta V by V, as delta V is the change in volume which is observed through stress. So, till now we have discussed what is stress, what is strain, and what are the types of stress and strain. And now we will focus on stress strain relationship. Okay. And for this we will discuss induced stresses. Induced stresses means the stresses which are made in the system, which are induced, which are formed in the system or object. For that case, elastic deformation is induced by a load such that when the load is removed, the part resumes its original shape. So, here we have elastic deformability, where when we remove the load, the object will come to its original shape. Okay. So, that is basically elastic deformation. However, when we have different operation or services in different parts of the equipment, there are different stresses which are available or which are made in the object, and these stresses are found due to different loading conditions, and these stresses are tensile, compressive, shear, bending, torsion, etc. So, all these stresses are induced in the system when we apply the force, but when we remove that force, all that stress will go out and object will take its original shape. So, materials undergo strain when they are subjected to stress. Okay. So, when we apply the stress, strain occurs in the system. And in this slide, if you see here, I am having a particular graph where stress and strain relationship are plotted for different material. On y axis we have stress and on x axis we have strain, and that axis is x axis is broken because we need to show large scale at x axis. Okay. Now, if you observe all these graph up to certain value we have a straight line. Okay, if you see, this is the straight line, this is a straight line, and after that we have non-linearity in the curve. Okay. So, this elastic this linear or this linearity basically, so this linearity gives the elastic condition for each material, and that elastic condition vary for different material. For example, here up in first this curve only this section is linear, this curve we have this much linearity, and similarly for grey cast iron we have highest linearity. Okay. So, each object will have certain linearity, and then the deformation whatever happens that will be permanent. Wherever it is linear, it is basically fall in the region of elastic deformation. Okay. So, we will use this point to derive the mathematical expression of stress and strain relationship. So, suppose a material is subjected to a uniaxial tensile load. Okay. We have applied tensile load in one direction only. It will deform in a manner characteristic to the material. So, according to the material, uniformity takes place when I am having uniaxial tensile load to a particular object, and that characteristic will depend on type of material. Okay. So, examples of possible behavior is linear when the material obeys the behavior linear elastic. So, in the last slide we have discussed that each material have certain linearity. Okay, that linearity section may be small or larger, that depend on type of material. Okay, but each material have this linearity, and which we call as linear elastic behavior, as shown in this particular figure, where we have the strain and stress and linearity occur. So, this means that stresses and strain are assumed to be related by Hooke's law. In its simplest form, Hooke's law can be stated as where the constant is known as an elastic modulus or simply a modulus. So, till the material follows linearity, that stress and strain can be represented by a particular constant. Okay. So, according to Hooke's law, we have stress divided by strain, and that should be equal to constant because linearity occur. Okay. And that constant we basically called as modulus of elasticity or simply the modulus. If in this case, that is sigma by epsilon, sigma is the notation for stress, epsilon is the notation for strain, and that will be equal to E, where E is the modulus or modulus of elasticity. Okay. If force is applicable in x direction, it means if normal stress is applicable in x direction, we can have the expression sigma x by epsilon x, and that would be equal to E. Okay. So, next parameter which I need to define is the Poisson's ratio. Okay. So, let us focus on this definition, and then I will explain what exactly it is. So, when a specified segment of metal is loaded in one direction only with resulting induced stresses and corresponding strain, strain is also induced in a direction or directions at right angle to the induced stress. Okay. So, what is the meaning of this? That we can understand through this object. If you see, this is the 3D object where this is the x axis, this is y axis, and this is z axis. If I am applying stress in x direction only, so what happens? Length in it, if I am applying load in x axis, it means if I am pulling it in x axis, it means tensile stress will be applicable in x axis. What happens? Length along the x axis will increase. Okay. However, we can also observe change in y and z direction. So, in x direction we have the strain, along with this we have strain in y as well as z direction. Okay. So, that basically when we stretch from one side direction, another two direction will have the reduction in their respective length. okay. And that you can also understand through this particular image. If you see, this is that red section, this is basically the original shape, okay. And when I am applying force in x direction, if I apply tensile stress in x direction, length in y as well as z direction will also be decreased. However, length in x direction will increase. So, though stress is applicable only in one direction, but it affects another two directions also. And here I am having another image where the original shape is this, where original shape is this, and from both side I am compressing this, okay. Stress is applicable in x direction, but it compresses. So, final length would be decrement in x direction, however, increment we can observe in y as well as in z direction. This is the direction, okay. So, that is the phenomena when stress is applicable in one direction only. So, experiments have proved that such axial elongation is related to corresponding lateral contraction. So, when I am having 3D object and force is applicable only in one direction, there will be elongation in that particular direction. However, contraction will occur in other directions also, whether stress is applicable there or not. So, ratio of these two deformation is a constant when it is falling within the elastic limit, and that constant is known as Poisson's ratio, okay. So, mathematically how we can define Poisson's ratio is that lateral contraction by axial elongation, okay. Lateral contraction by axial elongation is nothing but the mu. So, this mu is basically Poisson's ratio, and that depends from material to material. When I am applying compressive stress, that mu how we can define is lateral expansion divided by axial compression, okay. So, in Poisson's ratio we need to consider lateral divided by axial, whether it is contraction or elongation. So, here we have different Poisson's ratio for different material. So, you see for steel, which we will consider in manufacturing of pressure vessel, the mu value should be 0.3. So, here this table summarizes some of the values of Poisson's ratio, okay. And now we will discuss stress and strain relationship mathematically. So, first of all I am having biaxial system, and then we will focus on triaxial system. So, for example, if I am having this, I am taking example of this box again. What happens in biaxial system? It means stress is applicable in x direction as well as in y direction. So, this is biaxial system we are considering. It means stress is applicable in x direction as well as in y direction also, okay. So, what happened when I am applying stress in x direction, and that will be denoted as sigma x. I am applying stress in y direction, and that will be denoted as sigma y. So, due to sigma x we can observe elongation in x direction, okay. Due to sigma y we can observe elongation in y direction, okay. But at the same time this y will give some contraction in x direction, and similarly when I am applying force in x direction, it will and if I want to calculate the strain in y direction, there will be elongation in y direction due to sigma y and contraction due to sigma x. I hope you are getting this. So, if one refers to one direction as x, another direction is y, the unit elongation in x direction, x axis, due to tensile stress sigma y will be epsilon 1 equal to sigma x by E, okay. So, that is due to sigma x only. And tensile stress is also applicable in y direction, that would be sigma y, and elongation due to this in y direction we are representing as epsilon 2, okay. That would be the elongation, and due to this sigma y we have contraction in x direction, that is epsilon 2. Okay. So, that we can define as elongation in y direction epsilon 2 will be equal to sigma y by E. And along with this we have contraction in x direction. So, that we can define as epsilon c, that will be contraction in x direction, and that is equal to mu, that is Poisson's ratio, into epsilon e. Epsilon e is basically elongation in y direction. So, that we can replace with epsilon 2. So, here we have epsilon c equal to mu into epsilon 2. Epsilon 2 will have a particular expression, and that expression we can put over here. So, that is mu sigma y by E. So, resultant elongation or net unit elongation in x direction when both sigma x and sigma y are applicable will be epsilon x is equal to epsilon 1 minus epsilon c. Okay. That is axial elongation minus lateral contraction. We have expression of epsilon 1 and epsilon c. So, that we can put over here, where epsilon x will be equal to sigma x by E minus mu sigma y by E. Okay. And accordingly we can have resultant elongation in y direction as epsilon y equal to sigma y by E minus mu sigma x by E. Okay. Solving these two equations, we can have expression of sigma x as a function of epsilon x and epsilon y, and sigma y as a function of epsilon x y and as well as epsilon x. So, here we have sigma x and sigma y as a function of epsilon x as well as epsilon y. So, this is basically biaxial system. In the similar line, I can derive expression for triaxial system, where sigma x, sigma y and sigma z all three are applicable. So, in that case resultant elongation in x direction would be elongation due to sigma x minus contraction due to sigma y and sigma z. Okay. So, mathematically we can represent epsilon x as 1 by E sigma x minus mu sigma y plus sigma z, and in the similar line I can define resultant elongation in y direction as well as resultant elongation in z direction. Okay. After solving these three equations, we can have sigma x, sigma y and sigma z as a function of epsilon x, epsilon y and epsilon z. So, in this way we derive the expression for triaxial system also, and here we have mainly focused on tensile stress. However, all these equations are also valid for compressive effects. Compressive effects, how we need to consider that in compressive stress we have negative strain. Okay. So, that compressive stress as well as that strain would be represented by negative sign. So, it is only necessary to assign positive signs to elongation and tensile stress, and conversely negative signs to contraction as well as compressive stress. So, these points we need to consider when we have compressive stress and when we have combination of tensile as well as compressive stress. So, where compressive stress is there, take negative sign for stress and strain, and similarly in opposite to that take positive sign in tensile stress as well as tensile strain. Okay. And here I am stopping lecture 2 of week 1. We will consider discussion on stress and strain relationship in next lecture, and that is all for now. Thank you.